All right, so 25, is that the one closest to the pulley or the 15?
15 is closest to
And this one's 25, and then 15 hung? There's friction in this one or not?
Not yet.
Not yet.
Yes.
All right, so this problem is what you just did, really. I mean,
I had more
if,
problems with the friction.
I was gonna say the friction part is probably the part that would trip you up more. But I will do this part if you guys wanna walk through it. It's up to you. You guys are steering this. Your test is tomorrow. So I don't care what I do today. You should care. So who would like to see this first part without friction worked out? Okay. I'm going to set, again, if you're looking for where your mistakes are, you have an equation sheet tomorrow. That's largely of no use to you. You understand that, right? I mean, you have all the equations you want, but all that's necessary here is F equals ma. And that's all you're going to use until you get the friction. So the equations aren't all that valuable. It's a procedure, so start with the procedure. I think if there's no friction, it's pretty clear the system's going to kind of go this way. You guys all okay with that? So I'm going to establish that downwards is positive for the 15, to the right is positive for the 15 there, and to the right is, to the left is positive for the 15 and the 25. So everything I do from this point forward is going to establish that. I don't really care about the direction of up and down, whether that's positive or not, for these two on the table. I'm going to ignore the up and down for this particular portion because there's no friction. And friction is based on a normal force, but the normal force and the weight don't contribute to the motion of the blocks to the left. So all I really have to care about is the fact that there is a tension here, which I'll call TL, and a tension here that I'll call TR, T to the left and T to the right. Is that okay? So this block is experiencing a tension to the left, a smaller tension to the right, and that's it in the left and right direction. It's got weight and it's got normal force, but I'll come to that when we deal with friction. This block, the 25, has got just this TR. It's the force pulling it. Those are an equal and opposite third law force. Questions? All right. Box hanging off the table. 150 downwards. And TL upwards. We all good? All right, so free body diagram done. Next, apply Newton's second law, apply it to every object with mass. So that's our next step. And then, and applying that, these are all net force equals ma problems. So I need to add up all the forces that are equal to ma. For two of them, it's going to be like 150 minus TL equals m, which is 15a. And look, that's a lot. A lot of things put together all at once. You guys are doing a marvelous job of it, though. Now, the 15 is going to be TL minus TR equals 15a. And the last one's going to be TR equals 25a. Net force equals ma. Now, if you can get this far, you're golden. That's awesome. Because now it's algebra. People who got this far got at least 7 out of 10. Or at least, C-level credit for that portion of the problem. On the quiz, if you didn't, some of you didn't make it to case number 2, so I couldn't give you the full credit for making that a reasonable attempt, but this is what I'm looking for. Again, add all these together. And when you do, the TLs and TRs cancel, and I get 150. That's it's that 150 newtons hanging off the table that's causing the system to move. The other tensions are just connecting everything together. But the system has 25 plus 15 plus 15 amount of inertia times A. So 30, 55, so the acceleration here is 150 over 55. Is that 30 over 11? I think. Now, to get the tensions, you need to take this and plug it back here to get the tensions. That's not really the hard part of the problem. This part we just did, so it's very similar to what we just did. In fact, I'd say it's exactly what we just did, except this one wasn't hanging off the table yet. Right? If that one was hanging off the table, it'd be exactly what we just did. But then, friction gets added in, right? So same coefficient on everything?
Kinetic is 0.3 and static is 0.5.
Kinetic equals 0.3 and static equals 0.5. All right. Now, you don't know if the system accelerates or not. In fact, you don't know if it's enough to break static friction. That's what the rest of the problem is about, right? So will the system accelerate? And if you could break static friction, will it accelerate? So let's deal with the static friction problem first, but is there any follow-up to what we've just done? Because I'm going to reuse a lot of what's here. My formulas are going to have to change, but I can largely reuse my free body diagrams. I'm going to have to add weight and normal to both of these. They're not the same normal force, but I'm applying them individually to the masses. So I can say this is normal for the 25, this is normal for the 15, if you need to find a way to subscript it. And now, do you understand why I didn't want to use F for all the forces? F of n of 15, I mean, that's a lot of subscripting, so I figure this is better. In the y direction, N25 is going to be 250. They're going to be equal and opposite in the y direction. Do I need to go over that? All right. And normal for 15 is going to be 150. Now, here's the thing. Each of these boxes now has a static frictional force that is also acting in the system. That's two forces that pull to the right. Now, static friction, which means it's an inequality. So the first one's going to be 0.5 times mg, which is 250. And the other one's going to be 0.5 times 150. So this static frictional force has to be less than or equal to 75 newtons. And this static frictional force has to be less than or equal to half of 250 is 125. You guys seeing that okay? Now, both of these forces pull to the right. So the net force, I'm not skipping a step. I'm trying to maybe have you take a step back and remember what this is all about. This force right here, this 150, is pulling the system downwards with 150 newtons of force. That pulley means that it's pulling the system to the left with 150 newtons of force. However, the tension here is probably, if the system is not moving, the tension here is also 150. Static friction, if static friction's in place, then right now the tension in this cable has got to be 150 because the system's not moving and these two would have to be balanced. How much force can possibly pull to the right? Well, 75 plus 125. There's the possibility of a combined frictional force pulling to the right up to 200 newtons of force. Will the 150 that's hanging off the side be able to break static friction on its own? No, it can't. Because the static friction can get up to 200 newtons of force. So I think the system's going to sit right there unless you can break static friction yourself and get the system moving. Everybody follow that line of reasoning? Is that a reasonable line of reasoning? So that's how you answer that question. And yeah, I could see this question on tomorrow's test, perhaps not for as complicated an arrangement, but maybe for a slightly less complicated arrangement. Now, static friction portion of the problem. In the static friction portion of the problem, we say that static friction is broken. And then they go on to ask what the acceleration would be. Is that right? I don't remember the rest of this, but so if it's static friction and not kinetic friction, then it's slightly different. Kinetic friction is a constant. We can work this problem out. Let's just assume it's been given some velocity. You've tapped on the system, you've broken static friction, and you've given the system some velocity. Well, we treat this like a regular force problem now, just with more forces. So let's get ready. This one's going to be tough. I'm going to need to make this smaller to give myself some room. So let's do it with the box that's hanging. 150 minus TL equals 15A. The first box on the table, TL minus TR minus, I'll write friction, but for right now, just so I can give you guys a chance to keep up. Oh. Now, I'm sorry to do this, but we didn't get this part. This is going to be mu times 150, and this one's going to be mu times 250. This time mu is 0.3. Look, when you do this, you can make it all the way to the end. You have to ask yourself, when you work this out, is 150 minus both frictional forces going to be equal to 55A? Again, that's what you're going to get. If this is positive, the system speeds up. If that is negative, the system slows down. If it's 0, the system moves at constant velocity. But it can be any one of those possibilities, and I can see that being kind of a discussion question tomorrow. All right.